Thank you very much. I'm very impressed by everything that was before me, so I hope that I will stand up to par. And I can't see either slides, but I'll try to remember. So I belong to a consortium, Rafa Moonshine, and this is created by Sagi Gidali, who is here, and we are making progress on many fronts, and you'll hear some. So, and I'm a professor at Tel Aviv University, as was just said, and the entrance to the work was actually a finding that Sagi had when we met originally, and that NMN actually alleviates some of the STXBP1 problems. So we have a number of people that are working together. It's led by Hila Ben Moshe, as you can see here. And we have a paper under revision in Journal of Molecular Neuroscience. So this is our list of points of progression, our milestones of progression, or inches of progression. And we started with just looking, I mean, that's actually Sagi and Ella's work originally, Ella, his wife. And they are parents of Rafael, a very beautiful, young, handsome young man, and who is 4 years old. And the idea was to screen compounds that are either natural, like nature medicine, or drugs, FDA-approved drugs, and NMN, the precursor of NAD+, was actually found to be the leading compound. And it seems to be situated in a groove of the mutation of the STXBP1 that Rafa has, and changes, and maybe changes the dynamics of this the mutated protein and makes it more active. So that was the idea behind it. And here you see the precise docking, and you see, and I don't, the association of the NMN with the actual STXBP1 protein. So we went from there, and I should again say that it's Sagi and Ella went from there to actually develop C. elegans worms with the specific mutation that Rafa has, and saw that these worms were actually had problems in movement. And we saw that actually today before, in one of the lectures, that C. elegans is a good model to model the movement impairment with STXBP1 mutations. And what we are seeing here is that when these these worms are treated with STXBP1, they are actually recuperated from the movement problems. So the idea that it will address this specific mutation seems to be actually working. And then actually we met, when Sagi and Ella had all these results, we met. They came to my office, and I was extremely impressed by their by their charm, and by their idea that they need to find a cure for their son. And so what we did, we actually followed up Rafael clinically, together with Professor Yossi Levin, a collaborator of mine who is a psychiatrist, and we did what is called a Wineland questionnaire, and I think you are doing it here also. And we looked only at Rafael, and what we saw, to our amazement, is actually over a 2-year period, that actually his movement, his motor functions, both fine and gross motor functions, were actually developing faster than the historical cohorts that we looked at in the literature. And you can see that it on the slide that the motor functions were actually better with Rafael. We did one, so this is like between us, we did a Wineland questionnaire to another mature lady with another mutation in STXBP1, not like Raphael's, and we saw a similar effect. It seems that it is working on the motor function. So this is interesting. It needs to go, we need to go further into it. So the title of my talk is The Mouse. So the idea was that maybe we should develop a mouse model with Raphael's mutation so that we can test other compounds of interest, including NMN, and we can develop it better, and then we know actually how to take it to the clinic. And so we started I actually have a collaboration with in the Czech Republic, as you can see here, and we started the program by CRISPR-Cas editing, and we had a lot of death and problems in this. So the CRISPR-Cas was very simple, but then when we started trying to grow the colony, we had problems. So we were thinking, how can we solve this problem of premature death, and also the problem of the mice not getting pregnant. So sometimes this happens when you have transgenic mice, but this, we didn't exactly understand why it is happening, and we solved the problem, so you can maybe try it also when you do your own mice. So we did two things, actually. We used, instead of breeding with the usual mice that you use for generation of transgenic mice, we actually used the outbred ICR or CD1 mouse line, and we had success with this mouse line before. And also we found in the literature that NMN actually increases fertility in older mice. So we said maybe NMN will also solve this problem of not getting progeny, and we did an experiment and tested it. In terms of the ICR, this is something that I saw in my previous study, and I'm putting here one of my references. And in terms of the, it doesn't move. In terms of the NMN, I'm also putting a reference. But and so this is like the outline of what we got, and I'll go. Oops, sorry, and I'll go deeper. So we had like 4 groups, and we had two groups of control mice that are they have normal, healthy STXBP1, and then two groups of mutated mice. And we treated one group with the NMN for the breeding period, and one we didn't. And we saw that the NMN and also the ICR mating were actually very key to good propagation. So we are continuing with it. And you see it here as well. You see here the progeny results. And also we measured weight, just to see how well the animals are faring. And we saw some variations, but we didn't see an effect of NMN on the weight of the animals. So this is the conclusion, which I already said 3 times. So I recommend NMN in the breeding. And I also recommend to do this outbreeding with the CD1 or ICR. And actually, this will mimic more the situation, because always, when we speak about transgenic animals, they blame us. The clinicians blame us. You're working with one mouse. But if we do outbreeding and the mouse still maintains a phenotype, then we are much better, much more situated to reality. So this is, we did some sperm, cryo frozen some sperm. We brought them to Israel. And I don't know why I'm so, and now we have a mouse model in Israel, and I'm showing you results of the last 2 weeks. So I'm very thankful to my students, my graduate student, Jenna Kirchner, and my MD PhD student, Amos Gershevitz. And so I'm just showing you, as I said, it's very new, And I was afraid not to grow the animals on NMN so that we will get death. So the animals now are growing in the animal facility on NMN. I mean, they have NMN in their drinking water, and I'm now weaning them of the NMN to see the difference. But we still see a phenotype even in the animals who are growing in NMN. So what we are doing is catwalk. We are measuring the steps, the walking of the, as you see on the slide, we are measuring the walk, the way the animal walk, and we see a difference. So they are almost like the normals, but they are significantly different than the normal animals. And we also see a difference in the open field. And we also start, and this you see here, so this seems to be more active. And they are on NMN, so we still have a way to go. We have to wean them off the NMN and see how it goes. But they do have a phenotype in walking, and they do have a phenotype in terms of activity, and they're a little bit hyperactive here. And these are females, and the male cohort is not large enough yet. And we also have an indication that maybe there is also a problem in cognitive activity, but it's not, it didn't reach significance, so we still need to work on it. So the question is, did NMN actually improve the situation? So we are sure that it improved the situation in terms of the breeding. I have a feeling that it may have improved here as well, because we didn't get too many deficits in the catwalk, in the walking pattern, and also in the hyperactivity. But we need to check it, and there are room for other medication, which we are now doing, and you'll hear more about it maybe next time when we come and we have some more drugs to tell you about. So this is it for me, and it has been great work to work with the team. It's a fantastic team, and also to talk to you, and I'm extremely impressed. I come from a different syndrome, from a protein that I actually discovered. I called it ADNP, activity-dependent neuroprotective protein. There are less children, but you are a much more organized society, so congratulations. Thank you very much.
Thank you for that talk. Stuart Anderson, Children's Hospital Philly.
Could you speak louder, please?
Sure, or I'll bend down better. Stuart Anderson, CHOP, and UPenn. Both NMN and nicotinamide mononucleotide and 4-phenyl butyrate, which was mentioned earlier, both of them activate OXPHOS. And from the talk we just heard from Adam, which I'm biased for because he's in my lab, but one of the implications of slower docking is that it might be that enhancing energetics at the synapse could potentially ameliorate some of the effects. Wouldn't fix the underlying problem, but might make it less influential on circuit activity. I'm wondering whether in your model you would consider using other agents that also activate mitochondrial function to see if they also will have positive effects in addition to NMN. Things like bezafibrate or clinically approved enhancer of mitochondrial biogenesis, or other agents that are mito functions.
Yeah, definitely, and we're actually also looking at proteins that are associated with mitochondrial activity. We started looking. We actually also sent some tissue for RNA-seq, so we will definitely have, and I actually had it on one of my slides, so we found it like that, but because NMN is actually quite multifunctional, I believe that it's not just this association with STXBP1, but it's much more than that. So you kind of took the words out of my mouth. You're very right.
Great, all right.
Thank you. So, thank you. I manage always to give talks with no questions, so thank you very much for the question. Thank you.